Welcome to Chapter 5, Atmospheric Circulation and Wind Systems, Lecture 2. Last time, for Lecture 1, we looked at atmospheric stability, airflow over mountains and the rain shadow effect, lifting mechanisms, clouds, and precipitation. For this lecture, we are going to focus on global atmospheric circulation patterns. So what we're going to cover are cyclones and anticyclones. We're going to go into a little more detail on those just to get those kind of firmed up in your mind. We're going to go over global pressure belts and circulation cells, prevailing winds, those winds that come from a predominant direction in certain parts of the world, upper level winds, and seasonal shifts of pressure centers, because nothing can be just simple. We have to complicate it with those seasonal shifts. So starting off, let's recap a little bit on cyclonic and anticyclonic movement. Remember, cyclones and anticyclones are those large-scale circulations of air that are caused due to the movement of air from areas of high pressure to areas of low pressure. So starting off, we're going to look at cyclones. These are associated with areas of low pressure. These are low pressure systems. They are associated with unstable conditions. With a low pressure system, your air is going to want to rise. As it rises, it is going to create clouds. So if we have a very large low pressure system, we have a good chance of having a lot of cloud development and potentially a lot of storm activity. In cyclones, because they are low pressure systems and air is moving up from the surface, that air moves inwards towards the center of the low pressure, converges, that means all that air is coming together from all directions. When it converges, it has nowhere to go but up if we're at the surface, so it rises. And then also, very important to note, cyclonic flow, that spin that is created through the different forces like Coriolis force and friction and so forth, that spin for cyclones is counterclockwise in the northern hemisphere. Anticyclones are our high pressure systems. And in anticyclones, we are pretty much having stable atmospheric conditions. Because it's high pressure, it's suppressing that upward movement of air, so we don't get a whole lot of cloud development. So under anticyclones, high pressure systems, we get very stable conditions with very little cloud development and generally nice clear skies. In anticyclones, our air is sinking because it is high pressure. It is sinking, and when it sinks towards the surface, it moves outwards. It diverges away from that center of high pressure. And as it does so, because of Coriolis force in the northern hemisphere, remember Coriolis likes to deflect movement to the right, so our spin is clockwise in the northern hemisphere with anticyclones. This slide just summarizes everything I just told you. Plus, notice the caveat in red at the bottom of the page. The direction of spin is reversed in the southern hemisphere. So in the southern hemisphere, our anticyclones are going to go counterclockwise. Our cyclones are going to go clockwise. We're in the northern hemisphere, so you don't need to worry about that too much. Let's expand upon this idea of cyclonic and anticyclonic movement and this movement of air with high and low pressure just a little bit more to really get it firm in your mind, because that's going to help a lot as we move forward. So there's our basic recap of what's going on with high and low pressure systems. That's cool and all, but it's kind of esoteric. It is really hard to visualize what's going on with air because air is invisible. So let's kind of expand upon this idea, but using something that you are probably extremely familiar with, at least I would hope so, and something that's much easier to see. Water, and specifically water in a bathtub. So here's the scenario. You are going to take a bath. You draw a nice hot bath, tub full of water. You get into the bathtub and you are standing there, and then you begin to lower into the bathtub. As you lower your hiney down into the water that you are displacing as you enter the water is flowing away from that center of high pressure you are creating in all directions. So you sit down in the tub, and as that water is flowing away, think about what's going on in the water level of your tub. It's going up slightly. So you sit down, and you're sitting there for a while, and then you think, this water's kind of hot. Maybe I'll just stand up to cool off. So you decide to stand up out of the water. As you lift your big, bodacious, perfectly sculpted booty up out of that water, all that water that you had displaced is going to rush in. You are leaving a void where your body was. And that water is going to rush in to fill that void, that vacuum that you are creating as you lift up out of the water. We now have low pressure going on. So you stand up for a bit and you look down, and as you stood up, what's happened to the water level? Now that that volume that was your hiney is no longer occupying the tub, your water level has gone up. So that's one air mass or body mass, if you'd like, going up and down, creating high and low pressure. Let's complicate things. Your friend calls you up. Your friend likes water too. He knows you got a bathtub full of water, and he's like, hey, can I come over? And you're thinking, yeah, I like you and all, but I don't like you enough to share a bathtub with you. But I've got a hot tub. So your friend comes over. Now imagine this. You are standing at let's have you sit. You are sitting in your hot tub. Your friend comes and gets in, and he is just standing at the opposite you, on the opposite side of the hot tub. Let's imagine that simultaneously you decide to stand up and your friend decides to sit down. This is happening at the exact same time. What happens to the water in the hot tub? As he lowers himself down into the water, he is creating an area of high pressure beneath him on the bottom of the hot tub. That water is flowing in all directions out away from where his little hiney is about to drop down onto the tub. This is high pressure. As that water flows away from him towards you, and you simultaneously decide to stand up, as you stand up, you are creating a vacuum, a void, a low pressure area down at the bottom of the hot tub where you were just sitting, and all the water that he displaced rushes inward towards that low pressure center that you have created when you stand up. And what happens at the top? Because hold on, we've been thinking about this all in terms of what's going on at the bottom of the tub, which would be analogous to, say, the Earth's surface. Let's complicate things yet further. You are now Aquaman, and your friend is your Aqua Buddy. And the hot tub is now a fully enclosed tank of water with the water well over both your and your Aquabud's head. We've got a little bit of airspace between the very top of that water and the tank lid, just so we've got some space there for that water to slosh around. And now we are going to consider things from a slightly different perspective. Instead of focusing on what's going on at the bottom of the tank, let's figure out what's going on at the top of the tank, which would be analogous to the top of the atmosphere. Same scenario as before. You and your friend are going to move simultaneously. He is sitting on one side of the tank. You are standing on the other side. As your friend stands up, he is going to leave a low pressure area down at the bottom of the tank where he was sitting. But as he moves up that water column, as he stands up, he is displacing the water above his head now. So he's creating an area of high pressure because his head is moving towards the top of the water, and he's pushing the water out in all directions from him at the top of the water as he stands up. Meanwhile, you are sitting down. As you sit down, you are creating an area of high pressure on the bottom of the tank, but you've also created a vacuum at the top of the tank where you used to be, but now your volume is no longer there because you're moving down. This creates an area of low pressure at the top of the tank, so the water that he displaced by creating a high pressure at the top of the tank is now going to move towards the area you just vacated, which is now a low pressure area. What we have going on at the atmosphere is essentially the exact same thing that we had going on in the hot tub scenario. In this figure from your book, we have two areas of pressure. We have a high pressure center where air is descending on your right, and an area of low pressure on your left where air is ascending. How this works, once again, the descending air is moving down towards the Earth's surface. It is exerting a higher pressure at the Earth's surface as it gets closer and closer. That air is going to deflect in the northern hemisphere to the right of its direction of motion. So as it's descending, it is also creating a spiral, and that spiral is moving in a clockwise direction. Once that air from the high pressure hits the surface, the air that is displaced is going to be forced outward. It's going to diverge in all directions, still being deflected to the right. And where's it going to go? It's going to go to our low pressure center. These are our surface level winds. As that air from the high pressure flows inward to the center of the low pressure, still deflecting to the right, that is going to cause it, as it moves inward, to go in a counterclockwise direction. Meanwhile, our surface of the Earth is warming that air. Air is being forced inward. It is converging. It is being forced upward now. It's going to ascend, still moving in that counterclockwise direction. As it gets up to the top of the troposphere, we have a couple of different things going on. First, we've hit a cap. It can't go a whole lot higher. And secondly, it has cooled quite a bit. So I need you to now ponder this from a slightly different perspective. We are now in contact with a second surface, the top of the troposphere. So what started out as low pressure at the surface has now become high pressure at the top of our troposphere, because it is pushing on the top of the troposphere. It is displacing air. Our air is now diverging out from the center of this now high pressure system at upper levels and moving towards a low pressure center, which is now above what was the high. But as that air has sunk down towards the surface, it has created a vacuum there. This is now our low pressure center, and this causes our upper level winds. Think about the fact that as that air goes up from the surface low, it has been cooling the whole time it's been going up in altitude. Once it gets to the top of the troposphere, you know from past lessons that it is very, very cold up there. And as that air is flowing away from that area of high pressure, it is continuing to cool. As it cools, it becomes much denser. It is flowing into the vacuum that was created over on our right when that air was sinking. Therefore, it continues to suck air in towards the center of it and sink towards the surface. What we have just created here is an atmospheric circulation. Now we're going to take a look just at one more visualization. This might help you kind of visualize that spiral movement, because it's really hard to do just on a flat surface, but I think this does a good job. It shows the winds diverging away from the high as they spiral downwards towards the surface, and then they move in towards the low, and they spiral upwards towards the upper portion of the troposphere. This link that I have at the base, I would like you, if you are watching this, on YouTube right now to stop this video for a moment. Go visit the video that I have linked here at the bottom. This does a really good job of setting us up for understanding wide-scale atmospheric circulations, which is going to lead us into our next topic. I have this particular video, weather and high-low pressure, on our helpful video links in Moodle, and I will also have it linked in the description below the video I am currently narrating. Be sure to show the author of any videos cited here some love and give their videos a like, and consider subscribing to their channels. And then when you've finished viewing that weather high and low pressure video, come back to this presentation and we will carry on elaborating some more on atmospheric circulations and global pressure belts. So now that we are pretty solid on that background, we can move forward with global atmospheric circulation patterns, starting with global pressure belts. Global pressure systems are very large-scale atmospheric patterns of high and low pressure that influence climate and weather. These are not just your local highs and lows that will bring in storms or give you some nice weather. These are basically giant belts of particular pressure that encircle the globe. So global high pressure is a wide region where air sinks, creating very clear, calm, and often arid conditions. Low pressure belts are wide regions where the air is rising, leading to cloud formation and stormy weather. These systems are driven by the differential heating of the sun on the Earth's surface and the Earth's rotation, and these two things together create these consistent global wind patterns that will also create and add to these pressure belts. The global pressure plays a key role in determining global weather patterns in ocean currents and the distribution of precipitation over the surface of the planet. We have 4 of them to remember. We have 4 major global pressure systems that we're going to learn about. The ITCZ, the subtropical high, the subpolar low, and the polar high. Well, let's start out back at the basics. So let's find out where these global pressure systems arise and how they are created. Starting up, we have our basic image of the Earth here. We know that due to the differential heating of the Earth's surface, that at 0 degrees latitude, we are at our equator, we are getting the majority of incoming solar radiation. This is where the surface of the planet is being heated the most. Our air here is rising and creating a low pressure system. At the poles, this is receiving the least amount of insulation. The air is very cold, therefore it is very dense and it sinks, creating a high pressure system at the poles. We call the high pressure system at the poles the polar high. There's your first system. Because that pressure at the poles is high, that is driving air down towards the surface. When it hits the surface and begins to flow over the surface, it is going to deflect to the right in the northern hemisphere, to the left in the southern hemisphere, and this is going to get us eastward flow of winds. If those winds were going to make it all the way down to the equator, and they're going to be heading towards the equator because, well, that's where our low pressure system is. Because of pressure gradient force, our air is going to want to go from an area of high pressure to an area of low pressure. As it makes its way to the equator, it's going to continue being deflected in that direction. And you will see that at the equator, we have the same thing going on in both hemispheres, mind you now. So at the equator, that air flowing equatorward from the South Pole and the air flowing equatorward from the North Pole meet at about 0 degrees latitude. At the equator, they converge, and we know that when air converges, it is forced upward, In this instance, our equator is very, very warm, so the air is going to be rising anyway because it's much less dense. So we get this huge low pressure system, the equatorial low, at about 0 degrees latitude. You will also hear the equatorial low called the Intertropical Convergence Zone, or the ITCZ for short. We've already talked about this in one of the previous lectures about how the weather at the ITCZ is very warm, humid, and rainy. So let's stop and take a look at what's going on with our equatorial low and our polar high. At the equator, air is flowing upward from the surface. It is going to be forced towards the poles when it hits the top of the troposphere, the top of the tropopause, because our stratosphere is a temperature inversion. So it's warmer than the air that is meeting it at the tropopause, and it is going to put a cap on that airflow. So that air rising from the equator spreads out in either direction and moves poleward. As that air moves on its way up towards the poles, it becomes colder. And around 30 degrees north and 30 degrees south, it becomes so cold that it's dense enough that it starts to sink. So we get some widespread sinking air right at about 30 degrees north and south. And then once it gets down to the surface, some of it is going to start moving back towards the poles. This is going to create a circulation cell. We call this the Hadley cells. We have a Hadley cell from 0 degrees to 30 degrees north and a Hadley cell from 0 degrees to 30 degrees south. Now, some of that air that comes down to the surface at 30 degrees north and south is also going to be forced upwards towards the poles. On the surface, we have something a little different going on in the mid-latitudes we will get into in just a minute. But right now, let's focus on what's going on up our polar highs. Here, our air over the poles is being forced down towards the surface. It's going to go down to about 60 degrees north and south. It is warmed up slightly as it's headed down to those lower latitudes because there's a little more solar incoming radiation. There's also something going on with that stuff in the mid-latitudes. This is going to cause most of the air flowing down from the poles to go back up, be forced back up, and it's going to head back towards the poles. That's going to cause another circulation at either pole. These are our polar cells. So let's stop right here for a minute and backtrack and just take a quick look at the Intertropical Convergence Zone, the ITCZ, because this is our biggie. This is a huge driver of so many different things on the planet. It is a global band. We know that it's slightly discontinuous. It's broken up here and there, but for the most part, it is a global band of unstable buoyant air parcels that roughly track the equator and roughly track and definitely track the migration of the subsolar point. We will get into that more in just a bit. Because it is such a wide and incredibly warm area of uplift, and there is so much moisture there because remember, a lot of it around the equator is just ocean. We get a lot of thunderstorms and heavy precipitation. It's a massive area of stormy weather. So the unstable of that air of the ITCZ rises as far as the tropopause, once again because of the temperature reversion in the stratosphere. That is going to put a cap on the upward flow of that air, and it's going to, once it hits the top of the troposphere, or excuse me, the tropopause is going to have to spread out and go. It can't go down here because there's so much air coming up, so it has to spread out and move back towards the poles. That ascending air moves poleward. We are going to stop here for just a minute or two to watch this quick video with an animation that I think is going to really help you understand and visualize what's going on with Earth circulations up to this point. It's also going to set us up for what's going on in the mid-latitudes, because in the mid-latitudes, our air circulation results more from the dynamic forcing of air than from those thermal differentials. So if you are viewing this lecture remotely, please pause the video you are currently watching. Go watch the video that I have linked on your screen, and it will be on Moodle, also down in the descriptions below the YouTube video. And then when you're done watching it, rejoin us. And back to the lecture. Hopefully that bonus video helped reinforce your understanding of what is driving the Hadley and polar circulation cells. So what's the deal with the mid-latitudes? Well, as the upper level air diverges above the ITCZ, as it travels poleward, it becomes colder and denser. And right around 30 degrees latitude north and south, it has become dense enough that it begins to sink. When it hits the surface of the Earth, it diverges, it spreads out in all directions. Some of that wind, that surface wind, is going to be directed towards the poles. Some is going to be redirected back down to the equatorial regions. When that surface air in the mid-latitudes moves poleward across the mid-latitudes, right around 60 degrees north and south latitude, it is going to smack into that poleward air, that air from the poles that was moving towards the equator. And both air masses are going to be forced upward right around that 60 degree latitude mark. This is going to cause the formation of another circulation cell that we call the Ferrel cell. This is a dynamically forced circulation cell that actually works like a gear. It's not so much from the difference of heating and cooling, it's from air being forced upward or downward. And so it acts as like a gear or a cog in a machine that is helping to turn the other two circulations. What's going on at the Ferrel cell? Well, we have our descending air between the Hadley cell and the Ferrel cell. We have our ascending air between the Ferrel cell and the polar cell. Let's look at the descending branch there at 30 degrees north. What happens here is that descending and diverging air causes a third global pressure belt called the subtropical high. The subtropical high is a discontinuous belt of extremely dry, arid conditions and high pressure made up of a whole slew of anticyclones that is roughly centered on about 30 degrees north latitude and 30 degrees south latitude. Why is it so dry? Well, as we know, the air ascending over the ITCZ is creating a whole bunch of thunderstorms. So it is raining out a whole bunch of moisture. It's losing a lot of moisture right over the ITCZ. As that air, the upper level air, diverges and starts moving poleward, the further it gets away from the ITCZ, the more moisture has been lost. It is getting much, much, much colder and denser. And by the time it is redirected downward at about 30 degrees latitude, as it descends, it is being compressed and warmed adiabatically. It's being warmed a lot. And as it's compressed, what little moisture is still remaining in that air is, in general, squeezed out. There's not a whole lot of moisture left in that air by the time it gets down to the Earth's surface, and this creates our areas of these subtropical highs. What's the weather like here? It's generally hot, but almost assuredly quite dry over land. Right around the subtropical high, these belts, we have belts around the Earth. You can go look at a map and see where it is extremely dry, very arid. These are areas where we get our deserts, like the Sahara Desert. Over the ocean, well, we're not going to get a desert, but we are going to get areas of high pressure with very little wind going on. So to help you remember what the climate is like at the subtropical high, I have put in this picture of a desert. So back to our little map here. Okay, so there's 3 of our pressure systems. Now let's look at the other side of the Ferrel cell, where air from the mid-latitudes is meeting air coming down from the poles. It's converging, it's being forced upward. Note that this is the upward movement here is not necessarily because it's that warm there, because it's not that warm at 60 degrees latitude. This is a dynamic pressure system. This is one where it's forced air. Because those 2 air masses are meeting and converging, they are being forced upward. The Ferrel cell is basically just working like a giant gear. Where those 2 cells meet, the Ferrel cell and the polar cell, at 60 degrees north and 60 degrees south, that area of air being forced upward is creating low pressure. We call that our polar low, our subpolar low. The subpolar low is a belt of low pressure roughly centered on about 60 degrees north latitude and 60 degrees south latitude, made up of a whole bunch of cyclonic systems, those are our low pressure systems, that bring frequent precipitation. In fact, the subpolar low is where a lot of our wintertime storms in the mid-latitudes originate from. So, because it is associated with lots of frequent precipitation, I'm going to give it a little storm cloud to help you remember this. Our polar high, well, this is where we started out. This is an area of extremely cold, dense air at each pole that forms a zone of thermal high pressure. Do not be tricked by this word thermal. It in no way, shape, or form indicates anything warm is going on at all. This air is cold. It is so cold, in fact, that it can't hold very much moisture at all. So precipitation under the polar highs is pretty rare. And this creates polar deserts. These are deserts in every sense of the word. Just what you're used to in lower latitudes, except instead of sand, we have ice. So here's a little image of a polar desert to help you remember. I'm guessing this is probably Antarctica, which is a fabulous example of a polar cold desert. And I'm just going to add these little icons, these little picture images next to each pressure belt to help you remember the type of climate that is associated with each pressure belt. Next, we are going to look at these large-scale global surface wind patterns, the trade winds, the westerlies, and the polar easterlies, and then 2 special winds that have an interesting story behind each of them. The first is the doldrums. This occurs next to the equator, next to the ITCZ, and the horse latitude winds. These happen around 30 degrees latitude, around the subtropical high. We're going to use this map of the winds that's nice and I think really pretty clear compared to some of the other things that we've looked at, just to reference as we go through these. First up, we have the trade winds. These are those easterly surface winds found between the ITCZ and the subtropical high, so between 0 degrees latitude and 32 degrees latitude, both north and south. We have northeasterly trades and southeasterly trades. These are the most geographically extensive and consistent winds on the Earth's surface. They cover the largest amount of area of any of the major wind systems, and they're really very consistent. I mean, you can count on the trade winds to do their thing year after year, season after season. We will find out when we get into looking at El Nino that they will sometimes slack, like cut back a little bit, or sometimes they'll even reverse for a short amount of time. But they are very consistent, very dependable, so much so that we believe that the name the trade winds comes from the fact that sailors conducting trade in the tropic really counted on these winds if they could get those winds at their back, it would get them to their destination very quickly and with a minimal amount of effort. As those trade winds travel to the equator, they form a circulation loop called a Hadley cell. Right there's our Hadley cell off to our left. That Hadley cell is a continuous belt of air pressure, of circulation around the Earth in between 0 degrees and 30 degrees north and 0 degrees and 30 degrees south. Next up, we have the westerlies. These are our mid-latitude surface winds that come from the west and are found in both hemispheres between the subpolar low and the subtropical high. So, mid-latitudes, between 30 degrees north and 60 degrees north, and between 30 degrees south and 60 degrees south. The westerlies form something called the Ferrel cell. And our last major global wind system is the polar easterlies. We know that it is extremely cold at the poles because they're not receiving that much incoming solar radiation, and the air is very dense, and so it causes high pressure when it sinks. This sends air flowing outward, down towards the equator, away from the poles. It is deflected to the right in the northern hemisphere and to the left in the southern hemisphere, giving us in both hemispheres eastward flowing winds, the polar easterlies. The poles also have their own little circulation belt called the polar cells. So that was it for our prevailing wind patterns, our major wind flow at different wind belts across the face of the planet. Remember, we had two other small little specialty winds we were going to talk about, the doldrums and the horse latitudes. These two winds are basically a lack of wind. They are areas of very, very little wind flow, becalmed regions on the ocean. And these two cause some real problems for sailors. So the doldrums are a low wind region near the equator, basically underneath the ITCZ. The doldrums occur just because there's a general lack of wind, because the air right under the ITCZ is rising upward instead of flowing horizontally. So there's no real horizontal wind flow to speak of. And the doldrums, if you've ever heard somebody say, I'm in the doldrums, like I'm really down, well, that is a reference back to the lack of useful wind to move sailing ships to their destination. Now we have ships that are gas-powered, steam-powered. When we want to go somewhere, we've even got some nuclear-powered. When we want to go somewhere, we just kick on the juice. Well, back in the old days, your sailing ship was an actual sailing ship. You had to have sails to motivate back and forth. And for that to happen, you had to have wind. So when there's no wind, this is a real problem. This was really depressing for sailors. And so we have started to use the word the doldrums, the sailor's name for this wind, to mean being kind of depressed. Our second low wind region is the horse latitudes. The horse latitudes are centered on 30 degrees north and south latitude, directly under our subtropical high. Because it is high pressure and air is heading straight down, directly under that high pressure, there is very little wind flow. Now, once the wind starts to move away from it, we're going to get some wind. But right in the center, there's not much going on. The horse latitudes can be extremely arid over land. These are like our Sahara Desert. A lot of that is within the horse latitudes. Once again, kind of a problem for sailors. So over the ocean, there was a real issue. So we're going to stop for a minute and watch this quick video about the dark side, the dark meaning behind the horse latitudes and the doldrums. And here is just another map reminding you where our winds are. We have our polar easterlies, westerlies, northeast trades, southeast trades, westerlies, polar easterlies, and then our horse latitudes and our doldrums. There is another very short cartoon video that I have in the helpful videos that addresses the doldrums and the horse latitudes. It actually gives you a really good introduction to them in a fun way. It's only like a minute and 24 seconds long. I would suggest you watch it at some point. Here's another figure from your textbook showing you where those global winds are, and you can see your pressure cells. I would go through this again. You can even see the horse latitudes and the doldrums, I believe there. Yes, they are marked. You can go into your book and read about this in a little more detail. And this is just a cross section from, I believe it's from your book, showing if you were standing on the Earth's surface, looking at a cross section of the Earth's atmosphere, and you have your equator, 0 degrees latitude at your right, your polar 90 degrees latitude at your left. So you can see how each of these plays out. We've got our polar cell with our polar front. We have our westerlies, our trade winds, our polar jet streams and subtropical jet streams that we haven't gotten to yet, but hey, we are going to. Something that we haven't paid a whole lot of attention to yet is what's going on in the upper atmosphere. So we've done all this focusing on the circulations, but really pretty much from the perspective of what's going on down towards the surface. Let's take a look at upper level winds. So these upper level winds are winds aloft. These are winds that are above the influence of the surface. They're above the boundary layer, and they flow faster than surface winds because there's no friction to hold them back. They're not bumping into anything. Because we know that Coriolis increases with wind speed, that Coriolis effect of deflecting the wind one way or the other, it makes sense that it is going to deflect those upper level winds more than surface winds because they're going to go faster because there's no friction. Interesting thing about upper level winds here is that they flow mostly parallel to isobars. They don't flow across the isobars. Those upper level winds that do flow parallel to the isobars, we call geostrophic winds. Two examples they are showing you here are the upper level westerlies and the anti-trade winds. That are those upper level trade winds, but they're flowing in the opposite direction. So instead of flowing from the east to the west, they are flowing from the west to the east. Here's another example from our textbook trying to explain how those geostrophic winds work. Basically, it's what I just said, that air, as it rises from the surface, it's going to leave behind the drag of friction, which is going to increase its speed. We know that the Coriolis effect increases as we increase our wind speed. So at this point in the upper atmosphere, where there is not that friction to slow it down and the wind is moving really fast, Coriolis is going to be in balance with the pressure gradient force, and that's going to cause those winds to flow parallel to the isobars. How does that actually work? Let us take a look. So we know that in a non-rotating Earth, there would be no Coriolis effect. Therefore, our wind would flow from high pressure directly to areas of low pressure. It would cross those isobars in a straight line, perpendicular. There's no Coriolis going on here, no bending. It is strictly pressure gradient force. But then, if we take into account that the Earth is rotating, we will get that Coriolis effect, but the pressure gradient is still the dominant force here. So the Coriolis effect is in fact exerting an influence, but it's just enough to deflect that wind slightly so that it crosses those isobars at a slight angle. And not only does the Coriolis effect increase as we move faster, but it also increases as we move poleward. So once we get up towards the poles, our Coriolis effect is maximized. It is as strong as it can get. The closer you get to those poles, that's its max point. There's no friction to slow those upper level winds. And at this point, the influence of the Coriolis effect and the pressure gradient force are in balance. They are in equilibrium. They are both exerting the same amount of influence, and that causes the Coriolis effect to bend a lot more than it normally would, and it actually pushes that wind flow parallel to the isobars. We call that parallel flow of the wind flowing parallel to the isobars geostrophic flow, and the winds that are blowing parallel to the isobars are geostrophic winds. You have probably heard of the jet stream. Probably heard the newscasters say it on the news at some point. Jet streams, and we have 4 of them, are prime examples of geostrophic winds. So what the jet streams are these discontinuous bands of extremely fast flowing air found at upper levels of the atmosphere between 30 degrees and 60 degrees latitude in either hemisphere. So we have 2 jet streams in each hemisphere. We have polar jet streams that are closer to the poles, not surprisingly, and subtropical jet streams. The winds in these jet streams are crazy fast. They're away from friction, so because they're upper level winds. They are very, very narrow bands, and the narrower something is constricted to, the higher the pressure that's going to be, and it's going to push that air through faster. These things form in response to temperature differences between meeting air masses at these 4 different areas in the upper level of the atmosphere. Starting with polar jet stream, not surprisingly, located near the poles at about 60 degrees north latitude and 60 degrees south latitude. We have these extremely fast-moving bands of air in the upper levels of the atmosphere. The polar jet streams form where that cold polar air meets up with much warmer air coming from lower latitudes. That causes a big temperature difference, not surprisingly a big pressure difference, makes that air go extremely fast. The polar jet stream is used a lot by pilots, and it can be both a boon and a curse for commercial aircrafts. All of the jet streams, all of them, flow from west to east. So if a commercial air pilot is up in the jet stream and he is traveling the other way, if he's going from east to west, well, then that pilot is fighting the headwind the whole time, and it's going to really make it difficult for the plane to continue motivating on its way. If the pilot, he or she, can happen to hop on that jet stream going in the same direction as the flow from west to east, that's primo for them. That means not only are they going to get to their destination a little faster, it's going to save the airline a lot of money in gasoline because they are flowing with the flow, not going against the flow. And this image is just showing the polar jet stream. Here it's located at about an altitude of about 15,000 meters or a little bit over 49,000 feet in altitude. The fastest winds are shown in oranges and reds, and they can reach upward of about 224 miles per hour. So next we have the subtropical jet stream. Subtropical jet stream forms closer to the equator over the 30-degree latitude in both the north and south hemispheres. This jet stream forms when warm air from the tropics meets that cooler air from the mid-latitudes. Notice that both of these jet streams are located over some of our important pressure areas. with the polar jet stream located above that polar low at about 60 degrees latitude, and the subtropical jet stream located above that subtropical high that occurs at about 30 degrees latitude. Also notice that I have been saying these jet streams form around 30 degrees latitude and around 60 degrees latitude. I say this because those jet streams don't follow perfectly circular routes around the Earth. Instead, they kind of follow these undulating, meandering paths around. They still stay in that set range of close to 30 degrees north and south and close to 60 degrees north and south. But they do this series of undulations, like a series of ridges and troughs, that we call Rossby waves. A good way to visualize this is, imagine you are taking your dog for a walk down a sidewalk. You have the dog on a leash. You are following a fairly straight path on that sidewalk. Your dog, on the other hand, he's got to go pretty much with you and pretty straight, but he's on a leash and he's a dog. So he's going to stop to check out where some other dog peed. He's going to move forward a little faster maybe and then want to stop to say hello to somebody and wag his tail. He's going to see a cat across the street and really want to take off and veer to one side or the other. But he can only veer as long as that leash is. He's still got to stay on a reasonably set path. That's what's going on with our Rossby waves and the jet stream. Normally, you will have between, at any given point in time, 3 to 6 of these Rossby waves in the polar jet stream in particular. Here it says the northern hemisphere because we're just biased that way. But this goes on in both hemispheres. Let's take a look. So here, this figure is showing you what I just said. Notice our troughs and ridges. We can tell a lot about what the weather is going to be like depending on whether we have a trough or a ridge and how deep, how pronounced that trough or ridge is. With ridges, this is when your jet stream is bending towards the poles. Therefore, it's allowing more warm air to make its way further northward, and you tend to get fairly decent, fair weather. There's not a whole lot going on. It might be relatively warm. If you get a trough that is very pronounced, this is when that jet stream is meandering further down towards the equator. This is allowing an influx of more cold air from the poles. It's almost like somebody taking a cold icy finger and popping it down in your pudding. When you get these really deep troughs like this is what the newscasters are talking about when they talk about a polar vortex. It's these waves in the Rossby waves that dip very far down from the poles towards the equator. And here's that same figure that we saw from earlier with the polar jet stream. And notice where our little talk bubble is pointing. This is a ridge, this mountain-looking area where it has moved up towards the poles. This is where, beneath this ridge, we would have fair weather. Not bad, not much going on, not a whole lot of storms. On either side of that ridge, where it dips down, those are your troughs. That's where we are going to have unsettled weather, and it's probably going to be a little colder and quite likely stormy. It is important to understand that our global pressure systems, our surface wind patterns, even our jet streams are going to shift slightly north or south over the course of the year. And you've heard us say that it is discontinuous, some of these pressure patterns. They are stronger in some places than others. In some places, they may be totally absent at certain points over the course of the year. All this is governed by two things: the seasonal shift of the subsolar point and by the distribution of land masses versus water. So starting with subsolar point, because that's the biggie, your pressure patterns are going to migrate north or south over the course of the year based on where that subsolar point is. Easy way to remember this, your pressure belts are going to follow summer. This makes total sense if you think about it, because where our subsolar point is where it's going to be warmest, and that's going to start driving pretty much everything. So think of your subsolar point as a mother duck. If you've ever watched a mama duck with baby ducklings following her, they follow her everywhere. Like, she cannot budge 1 inch in any direction without them following her in a line. She goes north, they go north. She goes south, they go south. That's what's happening with the migration of the subsolar point. In the northern hemisphere, all of our pressure systems are going to move north in our northern hemisphere summer, because that's when the subsolar point is going to be furthest north. And they are going to shift south in our northern hemisphere winter, but it's the southern hemisphere's summer. So the subsolar point is the furthest south. All those pressure belts move with it. As far as the land masses, we know that water and land have different heating capacities, that water is going to take longer to heat up. It is going to take longer to cool off, whereas the heating and cooling of land masses is much more rapid and generally more intense over a short period of time. So that's going to also affect the strength of our global pressure systems. Now, this has some serious implications for our global precipitation patterns and our vegetation patterns, because these are mainly controlled by global pressure systems. And if those are moving up and down, you can imagine that there's going to be some sort of influence on the amount of precipitation, and the vegetation, the plants that an area has are dependent on how much water they're going to get, how much precipitation. So let's start this off by looking at the ITCZ and how it moves over the course of the year. The ITCZ is our biggie. This is our biggest, widest, most geographically extensive pressure system. So let's just work on this one. The way this works is the ITCZ is going to follow the movement of the subsolar point. But there's about a month of lag time, because as that subsolar point passes over a certain area and warms it up, it takes a little while for the ITC to catch up with it to where it really forms that nice full heating effect and allows the ITCZ to really just blossom and converge and move upward and cause all the clouds and so forth. So in July, our ITCZ is furthest north. It is at its furthest northernmost point throughout the year in July, about 1 month after the June solstice. In northern hemisphere winter, guess what it's going to do? In our winter, but the southern hemisphere's summer, this is where the ITCZ will be at its southernmost location. That's because our subsolar point has migrated down to 23.5 degrees south. It's their summer. We've got about a month of lag time before it hits that, and when the ITCZ actually catches up to it, so it is at its furthest southerly position in January. This figure from your book is basically showing you what I just said. But notice that the ITCZ is not a continuous straight line, nice and level across the surface of the planet, or around the planet, if you will, because it is a pressure belt. It's wiggly. Not only that, it's kind of discontinuous, because in some areas that low pressure and storms is broken up. And the reason for what you're seeing here is because of the differential heating between land and water. Notice that at its northernmost point in July, Northern Hemisphere summer, it's closer to the equator than it is towards the poles over land, over water. This is because of that differential heating between land and water. The land, when it is Northern Hemisphere summer, is going to heat up a lot faster than the water. This is going to cause the ITCZ to have lower pressure over these land areas. So it's going to be able to creep a little further northward over these. If we look down at the southern hemisphere in January, it doesn't go down quite as low below the equator in the southern hemisphere as it does above the equator in the northern hemisphere during southern hemisphere summer. Also, once again, because of the differential heating between the land and the ocean. There's more ocean in the southern hemisphere. Therefore, there's going to be less of a shift in temperature as compared to over land. Notice those deep bends towards the poles around southern Africa and just below the South American rainforest, and then just over Australia. It's bending a lot more towards the poles there because those land masses are heating up much more than the ocean around them. So, here's your question I want you to think about for the ITCZ. Ask yourself, what is the relationship between the ITCZ and the subsolar point? Why is the ITCZ confined to the tropics? Well, that one's an easy because it follows the subsolar point, and the subsolar point is confined to the tropics. When is it at its northernmost point? And what month is it at its southernmost point? And then be able to tell me what is the general climate like under the ITCZ. One thing I would also point out before we leave looking at the ITCZ is that these seasonal shifts of this warm, humid, rainy belt is going to have implications for the rainy seasons over land areas. Think about it. If your rainy season depends on an area of low pressure and a lot of cloud building, when is your rainy season going to be? It's going to be when the ITCZ is closest to your position. And you will probably have less precipitation as it moves away. That's going to have some real implications when we get into monsoon wind systems and precipitation patterns, which I believe we're going to touch on in the next lecture. And on that note of precipitation, let's look at some global precipitation patterns. What you're looking at here is a NASA image where our land colors on the land are in the colors you would see if you were staring down at the planet from space and there was no atmosphere or clouds or something to obstruct your view. What you're seeing here with our climate graphs, these are what climate graphs normally look like. What we have looked at so far has been a climate graph with just temperatures on it. Temperatures are that red curved line at the top of the climate graph. And we generally have our temperatures on the y-axis, on the left-hand side. But a regular climate graph also shows precipitation patterns as bars. Those are the bars you're seeing here in blue towards the bottom of the graph. It works the exact same way with precipitation, only the axis for this is on your y-axis on the right-hand side. That's going to give you your inches or millimeters of precipitation for each month of the year. How far the bars go up, if you've ever seen a bar chart, and I'm guessing most of you have, you know how this works. You can tell the monthly precipitation patterns for these different locations that are shown here. Now, the fact that they wanted to point out that this image is taken without clouds or an atmosphere to obstruct your view was kind of silly, because clearly you wouldn't have all of this going on in precipitation if you didn't have clouds or an atmosphere, but let's just go with it. So the way this works is these green colors that you were seeing there, these are very highly vegetated areas. They get a lot of moisture, a lot of rain. That's why they have so much vegetation. These tan colors are much drier climates where the air, it's more arid. It doesn't support this lush growth of green vegetation. So you are going to have less plants growing, and there'll probably be a slightly different kind of plant. We have just a couple more things that we need to bring into this mix, and that is something caused by the influence of these land masses with their lower heat capacity, so that they cool off faster and they warm up faster than the ocean. This is going to influence our overall pressure patterns to some extent seasonally. So over land, our seasonal heating and cooling creates these thermal low pressure regions in summer, because the atmosphere over the land is going to be hotter in summer than it is going to be over the ocean. And then thermal high pressure regions in winter. High pressure because that land is going to be colder than the temperature out over the ocean. These particular pressure regions created by this difference between the land and the ocean create something we call these semi-permanent pressure systems. These are pressure systems that just show up and leave seasonally in response to this differential heating between land and ocean. So these aren't like our pressure belts that are just there year-round all the time. They might shift up or down a little, but they're always there. These are things that will either strengthen areas of high or low pressure, that will either strengthen or weaken or sometimes disappear entirely at different points during the year. In North America, we have two semi-permanent pressure systems that we want to be aware of. One is the Bermuda High that brings summer precipitation to the east coast of the United States. And then the Pacific High brings aridity to the west coast of North America. And all of that has to do, even though they're both high pressure systems, it has to do with where are they picking up the air from and what kind of ocean current is it over. So let's see, let's take a look here. Alrighty, so what we have here is a map from your textbook. This is a very busy map, so I'm not going to go into too much detail. You can read this at your leisure looking in your textbook. But what's going on here? The map is showing us the average global sea level pressure over the face of the planet at different points of time during the year, different seasons. So right now we are looking at where the pressure patterns are in, what do we got here? January. And then finally, here we are comparing these summer precipitation patterns on either side of North America, determined by whether that side of the country or the continent is being affected by the Pacific High or the Bermuda High. Let's look up at our climate graphs here. This is the one on our left is for Los Angeles on the west coast. The one on the right is for Atlanta on the east coast. These two locations are almost at exactly the same latitude, and they're also almost exactly the same elevation. Los Angeles looks like it might have a little less variation in its temperature, but what we're interested in here particularly is the precipitation patterns. So look at our blue bars and how much precipitation they are getting at different times of the year. In Atlanta, this is on our east coast of the continent. It's getting its moisture. Remember, it's on a warm ocean current side. The Gulf Stream is there. The Gulf Stream is very warm. It brings lots of warm, moist air. So let's look at what's going on with our Bermuda High. It's a cyclone. It's a high pressure system. So it is spinning clockwise. So it's going along the Gulf Stream, and then it's coming up through the Gulf of Mexico. Yes, I said Gulf of Mexico. It is picking up lots of warm, humid air and carrying it in towards the center of the continent. That's giving us a lot of rain in summer. Now let's contrast this with what's going over on the West Coast in Los Angeles. If you look at our climate graph, you see that basically there is almost no precipitation whatsoever in June, July, and August. Here we have our Pacific High out over the ocean. Same deal, but look where it's getting its air that it's bringing into the continent from along the West Coast. It's picking up its air from up near the very cold Gulf of Alaska, and then it's coming down the West Coast over the very cold California current. So that air that it's bringing in is relatively quite a bit colder than over the East Coast, and it's much drier. Look how much more arid, how much drier the West Coast is as compared to the East Coast. We have reversed seasonal precipitation. Ask yourself at this point, what do you think would happen temperature-wise on the East Coast? Because we know that the Gulf Stream is very warm and it brings warmer temperatures. What do you think would happen temperature-wise on the East Coast if that Gulf Stream stopped running? I'll just let you ponder that. And this is where we're going to end this lecture. The next lecture, we are going to look at different scales of wind systems.